The broadcast is now starting. All attendees are in listen-only mode.
Right, good afternoon, everyone. It is 12:59 Eastern Daylight Time. Just letting you know that you're in the right place if you're looking for Onshape assemblies for Solidworks users. We will begin in approximately 1 minute. All right, good afternoon, everyone. Welcome to the Onshape webinar, Onshape assemblies for Solidworks users. It is 1 p.m. Eastern Daylight Time. Good afternoon if you're on the East Coast. Good evening if you're in Europe. Good morning if you are in California. You are in the right place. This is scheduled to go for approximately 1 hour. It is being recorded. Just a quick bit of housekeeping to get things going. You are in a GoToWebinar. We cannot hear you. You are all on mute. There is a mechanism in your control panel for asking questions. If you drop the arrow down next to the questions title, you will be able to ask questions. And I'm joined today by a wingman, Tim Fries, who will be assisting me. There are quite a few of you. This was a very popular webinar. So housekeeping, this is being recorded. This is not a competitive analysis. It's a learning opportunity. I chose this topic because there's been a lot of discussion, both on the forums as well as amongst our professional users and our support staff. And we decided that this would be a good webinar to clear up some misunderstandings and perhaps give you some cool tips and tricks. This webinar will cover Onshape assemblies from the ground up. Many of the professional users have been through the boot camp. Anyone is able to attend boot camp and got an introduction to assemblies. This will go into a little more detail about them, especially transitioning from Solidworks. I personally am a former Solidworks employee. I was there for a little over 15 years, the last 6 of which I ran the technical side of the major account program. Disclaimer, assembly workflows are constantly under review, and it is likely that some of the things that we're going to show you in some of the workflows will change. I won't show you anything that will get you into trouble down the road. In fact, everything I show you is how I want you to work. Questions are welcome. Please, as I just said, type into the questions box, and Tim will do his best to answer those as we go through. All right, housekeeping aside, let us jump in. I'm going to minimize this a little bit and advance. So what are we going to cover? We're going to review the Onshape Part Studio versus the Solidworks multi-body concepts just as a quick reminder. We're going to go forward and cover putting things into an assembly, positioning, orienting, and fixing them. And then for the Solidworks users, a quick discussion about rigid versus flexible and a new concept, grouping. The actual mechanics of mating are different. We'll cover how and why when we get there, and I will compare and contrast them with the Solidworks workflow. And in fact, I've duplicated some examples in both systems. There are many concepts that are the same across both products, so I'm going to draw parallels where possible, including the ability to create things like mate references, and we'll round this out with some layout sketch examples. Okay, moving on. What I will not be covering during this webinar, the creation of animations, the use of mate relations, cross-document linking to build assemblies, named position views, in-context editing, and inserting standard content. They simply were outside of the scope of the areas that I wanted to clear up any confusion over. That said, I put some of these things on this list and then put brackets around them because I decided recently that I was going to show a quick example. It's not full-on training, but I will show you at the end of the presentation where there is additional reading material available. So let's start with the concept of an Onshape part studio. An Onshape part studio makes parts. They are not assemblies. So let's jump straight into CAD.onshape.com. I'm going to be using a number of documents as we go through this session today. So here is a document containing a project that I've been working on, and I happen to have as one of the elements, that's what we call the tabs along the bottom, a part studio that actually makes 3 parts. The 3 parts are called mounting ring, frame top, and frame bottom. In fact, there's also a surface and could include many other things such as curves. A part studio is not an assembly. A part studio is for creating parts. We typically say that a part studio will contain 1 part unless 2 or more parts are directly related. In this particular case, I've got the frame top, the frame bottom, and the mounting ring, and it's fairly easy to see that there is a square profile that is shared across these 3 parts. And I'm okay with putting all 3 parts in the same part studio. The downside is I now have 65 features, and it's not always clear which feature contributes to which individual part. That said, some of you may not have seen this. You can go to the filter, type colon, part, then the name of your part, and you'll see just those features that directly contribute to that part. And if I go back and change the name that I'm searching for to frame top, only 6 of those features directly relate to frame top. I change it to frame bottom, and it's 18 of those features. And in fact, there are some very cool searching and filtering criteria that can be applied there. We do describe this as a slippery slope. It's very tempting to say, well, all parts are related, therefore I should build them all in the same part studio. The disadvantage is they are not assemblies, there is no instancing, and there is no motion. Basically, anytime you start a second part, you should be asking yourself, do I really need to build it here, or are there other techniques such as layout sketches or in context? But here I am, and I have 3 parts in my part studio. So let's go ahead and put those components into an assembly. We're going to talk about inserting, fixing, manipulators, orienting, and inserting multiple instances. Let's go back to here. Let's create a new assembly. I'm making a couple. Now I'm going to use the insert dialog. Almost all the actions in Onshape have a keyboard shortcut. In this case, the keyboard shortcut for insert is I. So I'm going to be using these keyboard shortcuts. I'll introduce them once each time and then use the keyboard shortcut moving forward because it is the most efficient way of using Onshape. The insert dialog allows me to insert items from the current document, other documents, or standard content. For today, we're just going to be working with the current document. I can filter things. I can say just the sketches. Make this a little smaller. I was trying to make this nice and big for you. I can filter out just the sketches. I can filter out just the surfaces or just the parts. So one of the things that misnomers that people run into is the concept of inserting an entire part studio. I have the choice of inserting the entire part studio by clicking on the part studio here, or inserting the individual parts. The ability to insert an entire part studio is a convenience. There is actually no difference between inserting the entire part studio and inserting these 3 individual parts, meaning it is not parametric. If I add another component to the part studio, it does not appear in the assembly. The mechanism for inserting is basically clicking on the part and then dragging it to a location in space and dropping it. If I don't specify a location in space, an arbitrary location in space, the components will appear in the same spatial relationship to the assembly origin as the parts were in the part studio. I now have the 3 components inserted into my assembly. I can come back at any time and add additional components. So if I come down here and say I actually want another one of these, what's nice is it's actually frame top instance 1, frame top instance 2. Very easy to understand. Dropping components in the assembly, unlike SolidWorks, did not fix the first component. Each and every component has 6 degrees of freedom, and I'm free to pick up any of these and move them around. And I'm now going to introduce a new concept, the Onshape manipulator. Selecting any part by clicking on it brings up the manipulator dialog, and it's fairly easy to determine how this works. You have the linear modifiers, I have rotational modifiers, and I have planar modifiers. In this particular case, these squares mean a linear motion in 2 of the planes. And all of these parts are free to float in space. If I would like to position any particular component on the origin of the assembly, it's very easy. I will pick a part, and then you'll see that I have the manipulator. But if I want the center of this base to be coincident with the origin, I need to somehow attach this manipulator to the center of this base. And it's very easy. I pick up the circular origin of the manipulator, click, hold, and drag, and I will see a bunch of these points. We're going to talk a lot more about these points in a moment, but for now, just imagine there's sticky points, and here's one at the centroid of the face, and now that manipulator is attached to the centroid of the face. The manipulator still works in exactly the same way, except that the center of the manipulator is at the centroid. And I can now do things like right mouse button over the origin of the manipulator and say, move to origin. Now I still don't have this this frame top part aligned with the primary axis. It actually doesn't matter, but let's go ahead for neatness sake, align this so the front is front, left is left, and so on. So by right mouse buttoning over the arrowhead, you have the same align and anti-align concepts as exist in SolidWorks when you're creating a mate, right? Remember the 2 options, align and anti-align. In this particular case, I'm going to anti-align with Z, and now I have aligned this part with a center on the origin and oriented it relative to the other parts. There was no mate, I simply positioned. Notice here from the drop down, there are no mates created. I can at any time fix this component. Notice there's now a ground symbol next to this part. And if I try and drag it, you'll see that there's a ground symbol appearing, indicating to me that I cannot move the part. In fact, if I had a chain of parts mated together and I tried to drag the last one, the same ground symbol would appear, indicating that I could not move it because one of these parts has been grounded. So far, so good. I hope Tim's keeping up. Fix is valid in the assembly in which it is applied. This is a source of eyebrow raising until you realize what's going on. Let us imagine that I fixed all of these parts, and I can window select them. I can shift select in the feature manager. I can just say they're all fixed. Now they all have this symbol, and I think great, and I want to use this in a higher level assembly. And I say insert. I want to insert an assembly, and here is assembly 1, and I put it in here. I could potentially be under the illusion that these are all fixed in space. That is not the case. All Onshape assemblies are flexible by default. That's a change from what you're used to in SolidWorks. Notice that the ground symbol did not come up to this level, and that is intentional. Parts are only fixed in the assembly, at the assembly level in which they are applied. So I can fix this one, and you can see now that this assembly contains, the down arrow means something inside that is fixed, and this particular part is in fact fixed. I can drag all the others around, but I cannot drag this one for the same reason you saw before, that it is grounded. Why on earth would we do that? There's actually a very good reason. I can just jump forward 1 slide. All Onshape assemblies are flexible. Let us imagine that I'm building this radial engine. Each cylinder is the same subassembly, and at the top level it's been used 5 times, and each piston is at a different part of the stroke. If I am working on the piston assembly, I might not want those parts to be sliding up and down. I might want to hold them in a very specific location. So I might fix a particular component so that I can measure the distance, say, from the crown of the piston to the top of the head, and I don't want it to move. So for that reason, we allow users to fix things in a subassembly that are flexible at the top level. Let that sink in for a moment. Okay, so now let us imagine that I'm at this higher level assembly and I want two sets of those parts. I would like to suggest that it is better to insert the assembly. Let's say I want two of these. There's one over here and there's one over here. It is better to insert the assemblies because they have instancing, the bill of materials is correct, and it's far easier to manage, plus a change to the subassembly is automatically reflected at this level, versus, I'll just move these away, inserting the part studio multiple times, even though it contains exactly the same parts. So I could say insert the contents of part studio here, part studio here, and part studio here. Why is this less preferable? Well, the reason is now I have a bunch of parts that don't really form any logical product structure. It's much easier and comprehensible and workable to insert sub-assemblies. So I need to undo this. And by the way, one of the very neat things we did with this insert dialog is we accounted for fat-fingered individuals who might accidentally, having done a whole bunch of work inserting components from this document and other documents, accidentally hitting the X when they meant to hit the green button. I do this all the time. What's nice is you actually have 10 seconds to undo it, just like undoing an email you might have sent. So just in case you screw up, we give you 10 seconds to get back to that state. Awesome. And of course, I said that everything was associative, so if I come back to this assembly and move these, I fix them all, so let's unfix everything, unfix. Move this around, I know one of them is still fixed, yep, so let's just move these together. It is, of course, my expectation, and I'm avoiding actually mating these for now because I need to come back and add some mates. There you go, they're not in a horrible row. Come back to this assembly, and why did all these sub-assemblies not appear in a row? The reason is that all the sub-assemblies are flexible, and each part can be moved individually inside the sub-assembly. Okay. Now, obviously, a change to geometry propagates up, but moving them here does not affect their positions here. So now the question is, what would affect the positions in the parent assembly? Time to start talking about mating. Let's get rid of these. All right, mating. So the tip there is insert assemblies rather than parts. All Onshape assemblies are flexible by default. So what can we do to make them quote-unquote rigid? There is a concept in Onshape called a group mate. It's a special type of mate. It's actually the only type of mate that affects more than one part. It's extremely awesome, very efficient, and holds parts rigidly together. It is best for standard and purchased parts, things that you are importing and do not want to move relative to one another. Let's say that you download a stepper motor from your supplier. You don't want those parts floating around in space. You would apply a group mate. Group mate supersedes all other mates. If there are existing mates on a series of parts, the group mate will take precedence and hold them rigidly together. We'll come back to the best practice in a moment. So let's imagine here I am in this assembly. Let us insert the contents of this part studio. And I don't want them to go anywhere. I am going to select, it's a little bigger. I'm going to select the group mate. It looks like a picture frame. And I'm going to window select these components, and I'm going to say group mate them. And you can see that I now have a group mate that holds these together. If I move one, they all move. If I fix one of these parts, now none of them can move because they're all held in rigid spatial relationships relative to one another. And of course, this component cannot move. Let's give a real world example. I do this whenever I import components. I have a robotic arm here. It was imported as a Parasolid file. And of course, Parasolid is the same kernel that Solidworks is on, the same kernel that Onshape is on. In fact, we use many of the same components. Our constraint solvers, 2D and 3D, are the same constraint solvers as found in Solidworks. I have one part studio with all the parts, and I have 8 or so sub-assemblies. Each of these parts is free to move in space. I don't want them to move in space, so I'm literally going to walk through all 8 of these and Windows select, let's say group, Windows select and group. By the end of this presentation, we will have mated this entire robot together and it will articulate appropriately. I'm just introducing the concepts one at a time. Now the concept is the ability to keep the components in a fixed spatial relationship relative to one another. Some of you are probably wondering why I'm not fixing one of the parts. The obvious benefit that people assume exists is that by fixing a part, I keep it on the origin and that I'm somehow going to use the origin in a higher level assembly. This is not the case. Remember, all sub-assemblies are flexible. The part is not going to move off the origin in the sub-assembly, but can, because the origins don't appear in the parent assemblies, it's actually completely irrelevant, the location of the parts relative to the origin, so there's actually no need to fix one of the parts relative to the origin. So this, 2 more. And as you can see, it doesn't take long, and I wanted to do this in real time for you so that you could see how easy it is to bring in a fairly complex assembly and mate it together, because of course conventions like STEP and Parasolid do not support mates. And of course now these all move together, and we'll come back and we'll mate this robot up and articulate it. Good. So, best practice, do not group across sub-assemblies. There are a couple of good assembly threads on the forums, and this was a very specific scenario that came up. So I am going to, let's see, I'm going to leave this. I'm going to create a new assembly, and I'm going to insert this assembly a couple of times. First instance is the second instance. So far, so good. The parts are held in the same fixed relationship because the group mate is being respected. And just as a reminder, the only mates that aren't respected are the fixed. Fixed really isn't a mate. But now it is a not unreasonable thing to say, oh, I want to keep these in the same fixed relationship relative to one another. I'll go ahead and Windows select these. I say assembly 1 and assembly 2. The problem is I've now actually held all of these components in a fixed relationship relative to one another. Here is the problem. I say problem, here's something to be aware of. If I suppress this group mate and move one of these components and unsuppress it, it is not an unreasonable leap to say, well, it moved here, therefore it's going to move in all the parent assemblies that it's used in. This is not the case, because I applied a group mate that said all of these parts stay in the same fixed relationship, spatial relationship relative to one another. It does this because I told you that the group mate supersedes all mates beneath it, and it held the top part of the frame to the bottom part. If I want that update to propagate, I suppress this mate and then unsuppress it again. That allows that change to bubble up. Again, this is not a best practice. In fact, I just told you to not mate across sub-assemblies, or not group mate across sub-assemblies. And if you choose to do so, understand that a change to a sub-assembly won't propagate to the parent until you toggle the suppression state of that group mate. Tim is probably typing furiously at this point. Good. Here's your best practice. So let's talk about mating and a new way of thinking. I'm going to start by demonstrating why I believe that the Onshape mating strategies are superior. I'll find a couple of examples that I might want to show you. Let's look for, I like this one because it's well known to Solidworks users, and there is an engine, stern motor engine, that many of you are familiar with. So I'm going to search my documents for stern motor. It's just easier to do this. You open it in the new browser tab. So the Scorpion is a good one because you know how many mates it takes in SolidWorks because you've seen the demos over the years. And it is this front suspension is fully mated, so you know everything moves. I grab the end of this control arm here, the entire mechanism moves. It's actually a very complex assembly. In Onshape, it's actually, the two things I want to point out, it's actually much better behaved than in SolidWorks. For instance, this cross member has a ball and socket mate at each end. And in SolidWorks, if I pick it up and drag it, there is an infinite number of solutions for any position. And so the thing just spins around like Linda Blair's head. If you're over 40, you'll get that joke. So if in Unshape, if I drag it, it is actually very, very well behaved. And it's using exactly the same constraint solver. So the first thing is it's very well behaved. The second thing I like to point out is there are only 29 mates here. If you open up this assembly in SolidWorks, it's 83, I believe. So there's nearly a 3-to-1 advantage in terms of the sheer number of mates that you need to manage. So it's easier to build, and it's better behaved because there are, I'm using air quotes, fewer mates to solve. Obviously, we're using the same constraint solver, so mathematically it's the same thing. It's just a much easier definition that's less prone to bad things happening, like flipping around or things conflicting. Another example that I like to show people is the stern motor. It is actually a public document. You're welcome to pick it up. It's a data set that has been around the industry for a long time. Many people have tried it in SolidWorks. I have tried it in SolidWorks and was singularly unable in my entire time there to get it to mate and work because there's a counter-rotating balance shaft and there are ball bearings. So whenever I build an assembly, if you see it in block capitals, feel free to animate it. So I'm going to animate the rotational degree. I apologize, I'm not teaching you how to do animations, I'm just telling you how to make it work. From 0 to 720 degrees in 360 steps. This will go ahead and generate a full-on kinematic analysis. There are actually a whole bunch of things that I found really difficult. There's an intake cam and an exhaust cam. There's a tangent mate between these cam followers. So there's two tangent mates here, 2 tangent mates here. So there's 10 tangent mates at this end. There are tangent mates between the ends of the push rods here, and there are tangent mates between the rocker arms and the top of the valve stem. So it's actually very complex, and that's before you add in the additional complexity of the ball bearings running at half the difference in speed between the inner and outer races. So I had a lot of fun doing this in Onshape, and it really did convince me that this was a better way to go. If you want to do some fancy stuff, let's see if I can get this to do it. If I reset this, which is always a good tip, I can actually section this and have it animate. Let's see if I can get this to do it. Yeah, I animate this. 0 and 720 and 300 steps. Go. Yep. Let me just fix that. 4. And we'll animate it. Just if you didn't know that you could actually animate assemblies while it was sectioned, this works very nicely. So it is a public document. It's a fun way to look at the assembly structure. I had a lot of fun building it, and hopefully you'll be able to learn from some of the techniques that you'll see here. Okay. Good. So that is the stern motor. Have fun with that. So I believe it's a better solution. Let's go ahead and show you what's different. Here's a simple assembly. I built this in SolidWorks here at the office. Like most parts, it takes either 2 or 3 mates. So I'd have to say that the average number of mates needed was probably 2.5. And if you think about it, in order to put this peg in this hole, I need a coincident between the back of this peg and the back of the block. I need a concentric to hold this face, a co-radial with this face. and then I need a parallel to orient the flat against the flat here. And this is not uncommon, and it's just 3 complete mates that I need to add in Solidworks. The big difference between the way you mate in Solidworks and the way you mate in Onshape is to think about it in a different way. Think about 2 coordinate systems, one on each part. The coordinate systems then have a mate applied to them. That mate can have any number of degrees of freedom from 0 to 6. 0 means they're fastened together. In fact, it's called a fastened mate, and they cannot move. A single degree of freedom is like a hinge or a peg in a hole. We call that a revolute. And the takeaway is 99 times out of 100, you only need 1 mate between any 2 parts. I need to perhaps do this live for you. I'm going to put 1 mate between these 2 parts in Onshape. So I will come here and I will open this up. Comparison example. I'm not going to talk you through the mechanics. I'm simply going to add add the mates and position these together. And it is kind of a worst case scenario because the flats are at 2 different angles. So these are my mates. We're going to come back, but for now I'm going to say I would like to mate the back of this to the back of this, and I would like to then align using those coordinate systems. I'm not teaching you, I'm simply showing you. Align the 2 coordinate systems so that they are aligned. That's a single mate, and it's very resilient. Let me give you an example. If I go to each of these part studios and start throwing fillets on here, 10mm fillets on here, big. Come here and put some on here as well so we can change the geometry. Okay. Good. When I come back to the assembly, I totally got behind it. I actually know what happened. Let's see. The edge of that. The edge of that. Good. Way to go to make a hard fillet. Prove that this works. Realign. Secondary axis. Secondary axis. Okay. Sorry. I think the Phillips was not supposed to do that. That was a mispick on my part, but you get the idea. It's very easy to fix. So let's go back and talk about how all that happened. The way to think about it is I need a coordinate system that's attached, 1 on each part. To get to that point, we have to talk about a hierarchy. The hierarchy starts from the bottom and works its way to the top. The concepts that we're going to be talking about are mate connection points, or mate connector points, sorry. On top of that, we're going to build the mate connectors and then apply the mates. We're not going to talk about mate relations for now. A mate connector point is a point that is automatically generated on geometry to which mate connectors may be attached. So these are the sticky points that exist on every face, on every part. You will find them at the center of circular openings. You will find them at the vertices and midpoints of edges along a face. You will find them along the vertices and midpoints of edges and sketches. Sorry, vertices and midpoints on a face, and the edges of faces, at the end and the midpoints, and at the centroids of faces. So let's take a look at how we would use those to find the location for the coordinate system. And we'll talk about the shift key while we're here. I need to open another document because we're about to mate it together. I love how I can have all these data sets open and Onshape just carries on. It's just so awesome. So here is an assembly we are going to put together. And if I say that I want to mate, these are my mating icons. There is a keyboard shortcut called M. What Onshape is asking me is, where is the coordinate system? And when I hover my cursor over the face, it's showing me all those points that I could potentially attach a mate connector or coordinate system too. And as I move my cursor around, you will see that Onshape is offering me different things. So here is an edge, okay, and on that edge there's an endpoint, a mid, and another endpoint. Here is another face, and I have the four corners, I have the midpoints, and I have the centroid. Here is a face that contains, a circle, therefore there is a center here. This is actually the center of this edge, this fillet on here. And the cylindrical face actually has three mate connector points. One at the end of the cylindrical face, one in the middle, which is very useful because it's always in the middle, and one at the end. Now, let us imagine that I wanted to pick up the center of this big arc. Right, here's the big arc, and you can see that there is a mate connector point in the middle there. If I put my cursor over this face and then move my mouse towards the middle, you see it disappears. It's like whack-a-mole. Every time you move your mouse over there, it disappears. So the Shift key holds all the mate connector points present. I hold down the Shift key, now I can move around and pick the one I want. I do not have to have my cursor over it. It just has to be the closest one. And when it becomes the closest one, the mate connector moves there, and I simply click, and then I can let go of the Shift key. So that is how you select the location of the first of the parts that you want to mate together. That is a mate connection point to which I've applied a mate connector. And I can offset it. People say, what if there's a gasket? What if I need it clocked at 15 degrees? Yes, you can do all of that, and we'll go through some of those examples. So a mate connection point, connector point, are the sticky points on the geometry. If the geometry changes, the mate connector points move and the coordinate system moves. If you don't want the mate connector to move, then you would attach it to something that doesn't move, perhaps a layout sketch or the origin of the assembly, your choice. And I will show you how to do that in a moment. Okay. The mate connector, that's the coordinate system, it's the local coordinate system, and it exists on a face or halfway between two faces. And that's a very useful technique, and I'm going to show you that. There are actually two types of mate connectors. Remember, that's just a coordinate system. One is called an implicit. Those are ones that Onshape makes for you as you build mates. Or they can be explicit, meaning I am defining a coordinate system. Just like you would define a coordinate system in Solidworks, I can define it up front so that other people can reuse that. And of course, they can be rotated or offset from the mate connector points. A mate defines the degrees of freedom that exist between two mate connectors. These can be explicit or implicit, and all I'm going to do is apply a type of a mate. Oops. Wait for that to disappear. The degrees of freedom that exist between two parts in a mate can actually be inferred from the symbology here, the iconology. This is a slot mate. It has 1 degree of freedom. The pin can move up and down the slot. This is called a cylindrical mate and has 2 degrees of freedom, 1 axial and 1 rotational. What's nice is, sorry, every time I click on, try and get that to disappear, it advances. What's nice is once I add a mate to between two parts, I can change the number of degrees of freedom very easily. Why do I have this stop sign here? It's to remind you to stop the moment you try and put a second mate between two parts. As a general rule, you only need 1 mate between any two parts or any two sub-assemblies. It's very easy to cite specific exceptions. If you think about a material handling robot, all of the joints are a single degree of freedom, a rotational degree of freedom, but the end effector always keeps the item being maneuvered parallel to the work surface. So in terms of joint precedence, I need to arrange 2 of the joints to allow the item being handled to always remain parallel to the working surface. So there is a mate here called parallel, and it's the easiest example to give of when it's valid to add a second mate. In fact, I could have used the parallel in the example of the peg in the hole with the flat on it to align them, but strictly speaking, I didn't even need that. I could do it entirely with one mate and align the mate connectors. So what's the takeaway from this slide? Stop as soon as you try and add a second mate. Let's go through and mate this simple assembly. First thing I'm going to do is I'm going to position this bracket onto the origin. It is cleaner, but it actually achieves nothing in terms of geometry. It is cleaner, so I pick on this part, I grab the origin of the manipulator, I'll drag it to an obvious point, I will move this component to the origin, and I will anti-align this with Z. Now, of course, I have some nice orientations for my drawing, so this will be front, this will be left, and so on. And in fact, I don't have to, but just to let other people know which part I've built things on, I fix one part. Now it becomes clear what I'm building from. It actually does nothing in higher level assemblies, but it's a good visual aid for myself. I now want to put this sleeve at the end of this tab, and I'm going to hit M for mate. The default mate type is fastened, that's 0 degrees of freedom, which is exactly what I want. I'm going to come up to this part, and I'm going to select this flat face. Why would I select this flat face instead of the center of this arc or the end of this face? The answer is the center of this flat face will always be here. The end of this cylindrical face might not. What geometric condition might occur that would change it? Filleting of this edge. So a good pro-level technique is to pick things that can't possibly change. The center of this flat face is not going to change. And you can see that Onshape has already created my first implicit mate connector. And I'm going to come up here and I'm going to put my cursor on this face. I need to hold the shift key down because I always want to select the center of the opening of this face. Again, if I had selected this edge, that edge could move if the geometry is later filleted. So I'm going to select this face. I'm holding down the shift key. I am now selecting the center of the opening. And Onshape saying, I got this. Just like in Solidworks, you have aligned and anti-aligned, and the ability to clock. So this is actually a 90-degree clock. You can actually see the mate connector rotating. The RGB axes are X, Y, Z, mimicking the view cube here. RGB, X, Y, Z. Z is the 27th letter of the alphabet. X, Y, Z, Z. Awesome. It's like aluminium. Aluminium being better than aluminum. It's cheaper and stronger. All right, so that's in the right place. There are keyboard shortcuts for this. There is A for align, Q for clock, because we're here at Onshape, we're hooked on phonics. And when I've got it, I can say, okay, this is like a little head-up display, just like in SolidWorks, that keeps me in the command, and I'm ready to move on to the next part. So I want to take this slidey part, and I actually want a different mate type. Instead of being fastened, I want it to move relative to this plate. I'm going to say this will be a slider. It doesn't matter if I forget to change it now because I can change any mate type later. I'm just going to pick the center of this cylindrical face. Now I could pick the center of the inner or the outer cylinder here, but it's good practice not to create chains of dependencies in assemblies. If you ever saw me at SolidWorks World presenting at the AE workshop, I always used to say mate as high in the tree as possible. That's still true here in Onshape. If I want to attach it to this part, again, I can just put my cursor over this face. I'm going to hold down the shift key, and I know that this is the center of the opening on the plate, not of the sleeve. I'm going to check that that's the right way around. It is. Say okay. Let's do another one. I would now like to have a revolute, that's 1 rotational degree of freedom, between the center of this cylindrical face, and my cursor's over the cylindrical face. There are 3 options. There is this one, and then the one in the middle, and the center of this pin. I could pick this edge, and it's true, I could pick the outside edge of one part and the outside edge of another part, but it's not good practice because it's entirely possible that the distance between these 2 faces would change. I always want this linkage to be exactly halfway between them. So I'll go ahead and select that. And if I want to query the nature of the degrees of freedom that exist using this mate, I can always ask Onshape to show me. I just hit this play button, and yes, I got it right. It's a revolute mate, and it's going to spin around. So I'm just going to say OK, so I can sort of check to see where we are. Good. Now this next one is going to get a little tricky. I somehow want this lever to the center of the distance between these two holes to be along the center here. Great. I'm going to create an explicit mate connector. Up to this point, every mate we've created has created two implicit coordinate systems, one on each of the two parts. I can mix and match. I can use two explicit, two implicit, one implicit and one explicit, and that's exactly the scenario we're going to demonstrate now, because I need a coordinate system exactly halfway between these two faces. Here is an icon that looks just like the mate connectors you've been seeing appearing on the screen, and there is a keyboard shortcut for creating them, Control-M. I'm going to say Control-M. The default type is on entity. That means, remember I said that the mate connector appears on the face that you select? There is another option, between entities. Think of the mid-plane type mate in Solidworks. So I need to say where it's positioned. Well, that's easy. It'll be the center of this opening. Notice I don't say the center of the hole. That's very intentional. And halfway between that face and the face on the other side. So now I have that coordinate system here. And if the distance between these two faces changes, this will always be in the middle. Huh, that's kind of useful. So now I want a revolute mate between this mate connector. And by the way, in terms of picking, mate connectors take precedence over anything else. So even though I'm at, this mate connector is behind this geometry, my cursor is over it, that's the one that's selected. And if you're in any doubt, you can always read this box here and it'll tell you, hey, you selected mate connector 1 of this part. Great. It's saying now you can either pick another mate connector or I'll make one for you on the fly. Well, make an implicit mate connector, a mate connector generated on the fly at the halfway along this cylindrical face. Great. So now where are we? By the way, after a while, sometimes the screen starts filling up with mate connectors. There's a keyboard shortcut for toggling them. It's K for mate connectors. Remember, here at Onshape, we're hooked on Pahonics. When I toggle it, the default is turn them all on. I hit it again, turns them all off. Great. I just have one more now. I just need a revolute between these two. M for mate. I can, just in case I screw it up, let's say I selected fastened, and I wanted halfway between there and there, halfway between there and there. This linkage was pulled away from this part. Why is that? When I'm creating a mate, I am only solving for the mate I'm adding. It actually unclutters the screen. It lets you see the effect on just the part that you're mating without the added constraints of the other parts. If you want to see the effect on the entire assembly, just hit the solve button. It's a one-time solve. If I say OK now, remember I accidentally selected fasten. If I say OK now, I'm actually unable to move this because the two coordinate systems are held rigidly relative to one another. That's easy to fix. And if I wanted to know what the type of mate was, there is a keyboard shortcut L for look at the mates, I'm guessing. No, J. Of course it's J. And I can see the nature of all the mates in the system. This is a slider. This is a fasten. This is a revolute, and a fasten. Well, clearly this isn't going to move because this mate, if I click on it, you'll see a cross highlights the name of the mate and the two components that it mates to. Wow, that's a lot easier than in SolidWorks, quite honestly. So I want to change the nature of that mate. I put my cursor over the mate, right mouse button, edit fasten to. Notice I didn't have to scroll through a long list of mates. It's very easy to find the mates. And I'm going to say I want to edit it, and I want to change it to a revolute. And if I want to see if it works, I can just ask Onshape to animate it. Yep, that's exactly what I want. I'll say OK. And now, at least kinematically, this is operating correctly. Good. Just notice that I need to run out of time, so brace yourselves. Putting this handle on is very difficult. there is no orientation, no Cartesian orientation that will give me a mate connector exactly where I want. So we're going to have to get fancy, so are you. So the first thing I'm going to do is section this part, Shift X. It allows me to get to the inside of the part. And I want to create an explicit mate connector that is halfway along this cylindrical face. But look, the ordinate axes align with the ordinate axes of heaven knows what. Certainly not what I want. So earlier you saw me realign a coordinate system, and you saw that there were two options, a primary axis and a secondary axis. In Onshape, unlike Solidworks, up is positive Z. If you didn't know, in Solidworks, up is positive Y. I didn't join Solidworks until '97, so that decision had already been made. But in every machine tool and 3D printer in the world, up is positive Z. So in Onshape, the primary axis is Z. RGB, primary axis is Z, that's the blue one. That is the axis by default around which two parts will rotate. They rotate about Z by default. So I want this to rotate about Z, but I want this handle to align with the handle in the assembly. So I want to align the secondary axis, that is the R for red, with this edge. Good. So now you can see I have a coordinate system that is correctly oriented with respect to this part. And now I can use it for my mating. Remember I said when you're mating, pick precedence goes to the mate connector, which is nice because I can unsection the assembly. To section it, I'm just toggling Shift X, section on, section off, like wax on, wax off. And then I can now say that I want to fasten mate between this mate connector and here. In fact, I just realized that this is not going to work because there's no coordinate system that works on here either. So to reinforce the learning opportunity, I'm going to say I want the mate connector halfway between there and there. I want to realign. The secondary axis is going to be parallel with here. I can now say I want a fasten mate between this mate connector and this one. The world is good. Again, to reinforce the learning, K to hide mate connectors, and J to hide and show the mates. And we are done. Hopefully Tim is keeping up. The next question is, how do I stop this from moving? The answer is limits. So you decide what defines the limit. Is it the slider mate, or is it this rotational one? I'm going to do the rotational one. You could use any of these mates to define limits. The only trick here is people get confused. There is a minimum and a maximum. The maximum must be bigger than the minimum. That's the only rule. So I can't say maximum is -10 and the minimum is 10. Maximum must be bigger. So I'll say it can still be a negative number, but it must be bigger. Not in absolute magnitude, but the maximum can be -10 and the minimum can be -90. And the minimum will say -65. If you want to see it articulate through the range of motion, just hit the play button. Very easy. And I am now good to go between these limits. Awesome. Just going to have a quick check to see if Tim is catching up. Wow, he's had a lot of questions. Awesome. Good stuff. So that is that assembly. Moving on. Question that is commonly asked: where are my planes? Why do I not get the origins why do the sub-assembly origins not appear? Why do I not get the sub-assembly origins? Relax. We've given you a mate connector. Mate connectors are much more powerful than planes. In fact, there are 3 planes on each mate connector. If I come here, for instance, and start a new assembly, and I want to insert a part, let's take this plate. It's a nice plate. I'll sort of cock it over a little bit. Completely arbitrary orientation. So I want a plane that is offset from the origin on the front plane by 50 millimeters. It's very easy. I could use our terms, or I could use the terms you're looking for. I want to create a plane that is, let's move this away from the origin for now. I want a plane that is offset from the origin, and you can see as I move my cursor around, how the make connector is reorienting. So I'll say this is the orientation I want, and I want it off the plane offset by 50 millimeters. So each of these make connectors has 3 planes associated with it. So now I can say I want to mate between this make connector and the center of the opening on the underside here, and I'll flip it over. Great. So now I just offset this with a plane. I happen to have used a make connector by 50 millimeters. And I could say, I could even, if you really want to get pedantic, I could rename this, front plane offset. Because now I can make all kinds of things to that and offset from it. So that's why there are no planes in assemblies. You simply don't need them. As far as origins, this one does get a little more interesting. If I want to specify a defined location relative to, say, an origin in a part studio, I would do it with a mate connector in the part studio. And this lets me do a number of very cool things. If I come to this part studio, there is actually a bolt here. And this bolt can actually be inserted in one of 3 places. It could be inserted with the head flush to a part. It could be inserted with the head offset by an amount to allow the spacing for a washer. And I need to attach a nut to the other end. And I know that, say you're Disney and you need three turns of thread past the end. I can define all of that with mate connectors here in the part studio. So I could say I want a mate connector that's here. By the way, if you want to, in SolidWorks where there's that tack button that holds the dialog up, if you're transferring to Onshape, you want to do the same thing, it's Shift-Enter, which duplicates it. So you can see that's the first mate connector we created. Here's another one. And I want to offset this one by long Z by, say, 1/4 inch. Okay. And I'm going to hit Shift-Enter again. I want one offset from this endpoint by move 1/4 inch. But I want the primary axis to be the other way. So I'm going to rotate the coordinate system about X by 180. And now my 3 coordinate systems are established. If I wanted a mate connector at the origin of the part studio, it's very easy to do. And in fact, because I built this on the origin, I'm actually going to simulate it by starting a sketch and just putting something out here. I can actually create a mate connector, Control M, that is on the origin, but owned by a part. So when you create mate connectors in a part studio, there could be multiple parts. So there's this concept of own a part. Now, whenever I use this part, I will get that mate connector. So now you can start to think, oh, wait, when I put it in the assembly, I have a common point that I can mate stuff together with. And that's actually very, very useful. So we'll come back to that. I'm actually going to, I deleted it. So now I have 3 mate connectors on this part. I'm likely going to version this, if this is a standard part, to make it available by linking to other users in my organization. Let me show you how this works. If I come to this assembly and say, for instance, I want to insert this bolt into these holes, I might want Onshape to do the mating for me. In SolidWorks, it's called Smart Mating. In Onshape, it's called Snap Mating. With that turned on, when I hit Insert and then click on, for instance, the bolt, Onshape will try and mate this for me. It's actually very, very good. So if I come down to the center of this hole, I actually have a number of things I can control. The orientation of the bolt, I'm going to control with the A key, A for align. I'm going to control the clocking with Q, Q for clock. You can see the mate connectors rotating, but there were also 3 different mate connectors on that bolt. I'm going to use the control key to cycle through them to get the one that I wanted. In fact, that's the one I want. And I just click to say I'm done with that one, and then I can move on and do the others. Do I have to do all 4? No, I don't. because I can use replicate, which says, hey, I want one of these everywhere you see one of these holes on this face. And it went ahead and put the other fastened mates in for me. It actually duplicates the fasten being used. It duplicates the mate being used. Cool. Move on. Running out of time here. There's replicate. I promised you this is to remind me to go back to the robot. So now that you know how mating works, all that I'm going to do is come to this top level assembly, and quick as I can, I am going to mate this together. So I know, for instance, that I need a revolute between here and here. I know that I need a revolute between here and here. I know that I need another revolute between, nope, not there, there and there. And one between here and here. Why am I doing this? I'm doing this so that you can see how quick it is. And also I'm going to show you the different drag modes that exist. And the robot is good to show you this because there's a concept of joint precedence in robotics. There we go. That's right. Complete done. I think there's 2 more to go. Mate, revolute between there and there. And I'll fix this one. And I want a revolute between there and I forgot which one it is here. Like that. I can always change it later. Okay. So this imported robot, started as a parasolid file, has been completely mated. So let's talk about dragging and joint precedence. Sometimes these assemblies are very well behaved. What's actually happening, this is one of 2 drag modes that exist. And it says, do whatever you can to keep the thing under the cursor, under the cursor. I actually have no control over any of the other mates. In fact, joint precedence can actually make this kind of interesting. If I pull down, I might have accidentally done a fasten. Look at this. Tim is probably screaming at me. Let's change this to a revolute. And let's change this to a revolute. If I start moving some of these, I don't have any absolute control over the other components. I'm not sure exactly what's going to happen. So that's one of the 2 drag modes. The other drag mode is using the manipulator. So if I click on this part, and let's say I wanted to actuate this joint and this joint only, what I do is I pick up the origin and I drag it to the center of the axis of rotation. It isn't even on the same part, it's just the center of the axis of rotation. And now I have very fine control. This joint will articulate and this joint only. So there are 2 drag modes. One is the free drag, one is by axis or vector. So if I pick this up, I have no control, and you can see the other part turning around. And the longer the chain of mates, the less control you have. So if I wanted to make sure that that and that one only moved, I would pick this up, drag it to the, oops, pick up the origin, drag it to the center of rotation, and now I can move this joint and this joint only. Good. Layout sketch. This is this replaces like patterns of planes in an assembly. So let's make this happen a little quicker. We're running out of time here. My apologies. Let's come to layout sketch. Last one. those coordinate systems are very useful because I can attach them to sketches. So I have a part studio here with a pulley. Let's run through this. I'm going to create a part studio. It's going to have my layout sketch. Make this 200. Make this 100. Let's make all this construction geometry, and that's my layout sketch. This is what I'm going to share with other users to make sure that everything that they build is correct. So someone else is going to use it either in this document or another document by first deriving the sketch, layout sketch. I apologize for short-circuiting this by not naming these things. And now I'm on the top plane. I'm going to start a sketch. I'm going to put a rectangle. By top, sketch, rectangle. I'm just going to say that I want a 30mm offset from the layout sketch here and here. I'm going to extrude this. Let's go down. Say 10mm. Put some fillets on here. The trick for filleting is I can use the in but not crossing. It's exactly the same as in Solidworks. Right to left is in but not crossing. Left to right is in. Left to right is blue. In but not crossing. Right to left is yellow. In or crossing. Just like Solidworks. Let's call this the plate. Okay. Now I'm going to put that layout sketch in an assembly. This is actually a workaround until we can have sketches own mate connectors. I want the sketch, and I'm going to put mate connectors here, and I want another one. One entity, boom. Mate connector. There we go. Another one. Boom. Another one. Boom. Another one. Boom. When I version this document, this layout sketch is available to everyone. This is like creating planes in a part studio that you then put into an assembly. I'm going to create a new assembly where I'm going to use this. I'm going to insert my assembly. And I am going to insert the plate. And now I want to put my pulleys on these locations. So I'm going to need a bunch of these pulleys. I'm going to need one here, one here, one here, one here. I'm going to mate. I'm just going to do fasten just for expediency. Remember, picking the mate connectors takes precedence, so it's very easy. I don't have to worry about zooming in on geometry. Do it here and here, and here and here. Now I want to let's put one more actually. Let's say put this here, and let's put it at the origin. I want to mate between here and the origin of the part studio of the assembly. Good. Now I want to, in context, build the belt. So I'm going to say I want a new in context. This is like editing in context in SolidWorks. Part, and just like in SolidWorks where the parts gray out, I'm now building in context. This is a ghost of the assembly. So the first thing I'm going to need to do my belt is I need a plane that is halfway between the top of the plate and the top of one of these pulleys. I get the notification that the context was created. I'm now going to use the belt custom feature. There's all kinds of documentation on how custom features work. So the width is going to be 10 millimeters. The mid plane will be the plane I just created, and the pulley faces are going to be picked off the assembly. I want the belt to go around these two, around here, around this idler and then back around here. Let's call this the belt. And then just like in Solidworks, you say I'm done editing, it's called insert and go back to the assembly. The belt that I just created. And there are all kinds of webinars just on creating in context features. I'm actually going to change the color, just more visually exciting. So now let's talk about that layout sketch. We're going to come back to this part studio. Everything is controlled by this one sketch. If I edit this sketch and say that this is now 150, and this is 150, making it square, I could go to the intermediate step, so I can just go all the way back to the top level assembly. You see that everything's changed except for the in context. As you know, Onshape is different than Solidworks. In context doesn't update all the time. It causes too many problems with features and faces moving that you don't want. All I do is I say update the context, which updates the belt. That is layout sketches using assemblies. Let me keep going because I'm 10 minutes past. There have been multiple threads on the forums. I'm calling this the Billy 2 scenario. I'm not going to use his real name. He is known to me. He's actually a very cool guy. I'm not going to say the name of the company he works for. But he had these parts that he needed to mate and move relative to one another that had no obvious center. And he was right. And the reason I've been using these parts all morning is there is no obvious center. So if I want to create a new assembly, here are the three parts. I'm going to jump back to the part studio for a moment. There is no coordinate system that I can easily create on all three of these parts. If I show only this part, hide other parts, there is no, I can't get the center of this space because there are cutouts. The geometric center is not the same as quote unquote the center. So I'm kind of screwed. So I do call this the build 2 scenario. So what I did, it's very simple. All you do is create an identifiable position. Just one thing that you're going to base everything off. And I just created a sketch and I just put one point on it. Very simple. We're going to create 3 mate connectors because there are 3 parts, and each mate connector is going to be owned by a different part. So here we go. Control M. The location of the mate connector, the origin, is that point. The owner is this part. Great, done. Let's create another one. I want a mate connector that's on. I'm going to hide these as I create them. On this part. And the owner part is this one. Let's try that again. Here, and bottom frame. I'm going to hide that. And now the top one, Control M. Again at this point, and the owner part is here. And frame top. Good. I've got my 3 mate connectors. I'll turn them all on. So now I have a position that's common to all 3 parts. So I come to the assembly. I will insert the entire contents of the part studio. Remember, it's not parametric. I'm just going to say insert. I made this bigger. Let me reset that. All the dialogue is going to get smaller. Here it is. And I'm going to take the bottom one and fix it. Now it's really easy to mate all of these together. I say I want a fasten mate between, say, this one and this one. And in Build 2's example, these needed to move up and down relative to the bottom one. I have to keep trying not to say his real name. He's actually a very cool guy. So I'm going to say slider mate, and I want it between here and here. Now, why didn't this move? Because I haven't solved the whole system. Just to double check before I do it. Now you can see how it's very easy to mate together 3 parts that have no common obvious, a piece of geometry or location common to all 3. It's simple. You just make them common. What's nice also is that I can put limits on the slider very easily. The minimum is 0. Maximum always has to be bigger. So I'll say this is 75 millimeters, and I can have it animate between the fully open and fully closed. Now you can see, can't go any higher than that, can't go any lower than that. So I'm calling that the build 2. If you see him out there, tell him I said hi. Further reading, the Learning Center has some very cool tech briefings. You're free to sign up for the top-down class, but also don't forget there's a mating basics tech paper. There is an advanced mating tech paper, both of these written by Katie Huffman, who heads our training department. There's one on exploded views for assemblies, and there's one on how to use standard content. And if you have never been there, you need to log into an account that specifically I keep. He's a very, very bad person and doesn't use any of the training materials. And he doesn't come here very often because he goes to the Learning Center. You will see the available instructor-led classes, the top-down design in Onshape if you want to know more about the assembly capabilities. And if I come to the tech briefings, you can see the advanced mating techniques, the introduction to assemblies, exploded views, and a bunch of these written by experts in Onshape. And if I was to recommend one for you to read, I know it's under data management, but it should really be under assemblies. It's called the Product Structure and Organizational Tips, and walks you through how to build complex assemblies, how to manage them, and how to part out, meaning break down a large complex document. I'm way over my time. I've enjoyed presenting to you. Hopefully Tim has been able to keep up with the questions. And if you want to contact me directly, my email, not that I recommend contacting me directly, I suck at returning emails, but if I go all the way back to the beginning, you can follow me on the Twitter, and my email is pthomas@onshape.com. Thank you very much. Thoroughly enjoyed our time together, and please carry on using Onshape. Tell your friends about it. It really is awesome. Thank you very much.